I feel like David Beckham being on the bench sometimes. The other members have done far more than me. My responsibilities in New Zealand, my family situation and so on, meant I couldn't come for long periods, and I'm grateful that you still left me in place. You really could have pushed me out. So I'm very grateful. And people like Henning, John, Bruce, Tim and Mark have really done all the hard slog. So they must have more patient wives than I have. So there we are. There are two giveaways for this talk. One is immodestly from my centre, the Centre for Maths and Industry, which is one of my major activities. I'll tell you a bit about it as we go along. That's this little brochure, and you're welcome to plagiarise it. I was pleasantly surprised to see when I was in Singapore earlier this week that the Malaysians have plagiarised it, and they said, "I hope you don't mind." I said, "Of course not. It's part of this planting activity." And there is also an article by me, which is your takeout from today. Have you all got one? Which has the title of my talk. It appeared last month, if you want to quote it, in the Gazette of the Australian Maths Society. Okay, I'm a great fan of this activity. It's been my life mission really to do what I'm currently now doing, and let's hope I'll be able to continue to do it for some years. Being an adjunct professor in Oxford has given me an insight to how they operate there. The OCIAM, Oxford Centre for Industrial and Applied Maths, recommend you visit there sometime, and it's now funded, very well funded. OCAM, which is the connection with Saudi Arabia, of course, the Oxford Collaborative Centre for Applied Maths, I think it calls itself. And these centres now have got a mission to plant the activities right round the world. And I'll tell you a bit about that as we go along. My centre's now got this website, and you're welcome to visit and plagiarise materials, download materials from it. And there's the Oxford maintained website, which has study group reports from all the study groups around the world, hundreds and hundreds of them. When I was in Thailand last December, I noticed that there were graduate courses based on that stuff in that website. Sorry, that one there, www.mathsandindustry.org. It's very easy to navigate. You can navigate by type of problem, location in the world. If you want to do something about heart attacks, you just Google heart attacks and you'll find someone who's been working on that and a report about some aspect of it. So that's what I want to talk about now. I've taken a special interest in our near neighbours. I call Korea a near neighbour, I think, though after a day of flying, I'm not so sure. But, and certainly we have been very successful in Southeast Asia. There is study groups now starting in Malaysia, which we have nurtured, and there's an increasing activity going on in Singapore, which is where I've just come from yesterday. So that's my introduction. Now, does this work? Or what did it picture? Maybe not. There's the references. The first one is my own article, and I want to point very strongly at those two OECD reports. You wouldn't believe it, the OECD actually does something useful. It has a global science forum, and it works collaboratively across the 28 countries of the OECD, which Korea and New Zealand are members. Perhaps we don't really qualify, but we're there. China is not in it, but it was involved in the activity I'm going to talk about it. And that number 2 is a survey they did in 2007-2008 of industrial mathematics as a discipline. It basically gave nice definitions about what it is, why should you do it, what it's all about, and how it distinguishes itself from even applied mathematics, which is a very fine distinction, of course. So I recommend you read it. I've actually brought copies with me, and I can show you, well, you can download it yourself. After it published that report in July 2008, the Global Science Forum formed an international committee with all the 28 countries able to be represented. There was no one from Korea, which I was disappointed about. It was actually chaired by Dr. John Ockenden from Oxford, and countries were enabled to nominate people to that forum. New Zealand didn't do anything about that either, but I was very flattered that the Australians nominated me, so I had to become an honorary Australian. After they'd done that, the New Zealand government people got in touch with me and said, could you now represent us? And I said, well, provided you pay half the bills with the Australians, and of course they did. So what we did over the following year, from July 2008, we gathered an audit of the 28 countries about what was happening. I took the liberty of mentioning the IMI in Korea, so you'll see that in the third report you're mentioned, because I was actually on that committee representing 2 countries, Australia and New Zealand. It's a living document, number 3. It's being updated as countries add their activities. So if you have significant developing events in Korea, you should certainly add them. It's all very self-evident when you get there about how you do that. So we got some criticism. Some countries wrote to us, or some universities or organisations wrote to us and said, hey, you've missed us out. We didn't try to be that comprehensive. We just tried to be illustrative. But of course, when people ask to be added, we do that. Whoops, that's back, so that's forward. Now I've got it. The 2 things I want to concentrate on today is the planting activities, and I'll give some summary documents from those reports. And then, because I had so many things I wanted to tell you, Yong-Jung suggested I take an illustrated problem from a recent study group, so I took the one that I was moderator for in February of this year, which is very unusual. And it's one that you had to work very hard to find the mathematics in it. So topic 1, the planting of industrial mathematics. First thing is, we've got to remember that industrial mathematics is a distinctive activity. What's its main distinction? It starts and stops with the client's problem. It's driven completely by what your client wants. It's no good abstracting the problem, making it neater, more attractable, more easy to do. It's important, I think, to stick to the client's problem. And of course, that's what my centre, which after the MISGs left New Zealand and went back to Australia, because we shared them, that's my banner over there. I hope you were impressed by it, because I had, I got detained in customs bringing that thing in. It looks like a machine gun when it's closed down. So I had to unfold it in one airport. But here it made it. We are basically an interface with Australian and New Zealand industry, trying to get problems, set up teams. Mark was in one recently with Fisher and Paykel about the dynamics of a washing machine, all the vibrations you get in the spin cycle, and we had a lot of fun with the hot bifurcations that occurred in that, didn't we, Mark? Yeah. I don't think we're going to talk about that one here. And again, I say you should look at the Oxford website to see for more examples. Right, well, I'm now explaining further what is industrial mathematics. It's a means by which industry improves the quality of products. It starts with a problem posed by industry. It should be an equal partner as a subject with science and engineering at all stages. And it must be meaningful to the industry and the non-mathematical personnel. And you've got to solve the problem as stated. Hopefully, it will include advances in mathematics. I'm currently trying to get a book together which I'm going to call Non-Local Calculus. It is functional differential equations in a part, but there's surprisingly few applied books in this field. There's a few very good theoretical ones, but that came about because of my work in plant growth, tumour cells and so on, and I would never have got some of the nice results that Bruce is doing now and we're going to talk about if I hadn't been stimulated by the need to model plant cell growth and tumour cell growth. Okay, now when I'm talking to academics, they keep asking me, why should I do it? Well, I think there are some incentives there. There's the relevance of expertise to real-world applications. There's the satisfaction arising from knowledge transfer and interesting new problems like my non-local calculus. I spend all my long plane flights doing problems like y dash t equals y of alpha t, which if you go to T in any university maths department around the world to make them keep quiet, you ask them, how do you solve y dash to t equals y of alpha t, where alpha is a real number, positive real number. Yeah, it's interesting that problem, and when alpha is 1, of course, the solution space is of dimension 1. But alpha is not 1. It has an infinite dimensional basis of solutions. And you could, just think how the small changes led to a much richer problem. And there's a prize if you can do the solution by lunchtime tomorrow, so don't show them, Bruce. You're not eligible. The financial gain, of course, is tremendous. When my centre was formed in 2003, the university said, right, you can have 3 years probation to get it going, and if you're not making money by the end of 2006, it'll be closed down. That was quite savage. Massey's a tough place, isn't it, Bruce? It was a trial basis, and we were fortunate, of course. The Australians helped us greatly by giving us the hosting of MISG for 3 years. That really got us launched. They gave us another 3 years till 2008, and the probationary period is over, and we passed, and we weren't executed. It's now set up for impermanence. And so, provided it keeps making money, I guess they'll let us carry on. There's another big initiative on the WINS that we want to actually extend it into a centre of excellence for the whole country, and take it on board, but there's a lot of negotiation to go on there. There are disincentives that our bosses sometimes say, or particularly our heads of departments might say, it's not new mathematics. You're just doing old mathematics, maybe in a new situation. And I've seen that on the reports from research grants that I've put in. This guy is not doing new mathematics, he's just doing old mathematics in a new situation. Fortunately, I've got used to being told off, so I just ignore it. But it is sad that there are people out there who see it like that, and that's a difficulty. And perhaps that would make young people think again about getting involved. Perhaps I won't get promoted if I do this, because in many countries, I don't know what it's like in Korea, really, the rating that you have or the standing you have is a function of your research and teaching, and consulting may be not an independent variable. And so therefore we've got to get that changed. Now, I've worked very hard with our government people in New Zealand to get that changed, and I think I'm winning. The new PBRF rounds will have consulting as the third variable in my statement on the last line there. Research, teaching and consulting. Perhaps we should put consulting as first. So just be aware that that kind of climate does exist by the pure end of our subject. Industry, of course, asks me lots of questions. I spend a lot of time in boardrooms and chief executive officers trying to answer their questions about how we operate. Is it really relevant, they say, to industry? They don't understand it. I remember one chief executive saying to me over a cup of coffee, I spent all last night trying to tell my daughter about solving quadratic equations. The daughter was only about 14. I managed it, he said, after a lot of difficulty. This guy was earning a big salary, but he had trouble with quadratic equations. And then she asked me, why do I need to know this? And that's a question that you'll get at all sorts of levels. They'll ask, how do I get value? Well, you deliver, I guess. How does it work? How much will it cost? Why can't I have it now? There's no good saying we'll do a PhD in this sometimes, and we'll tell you the answer in 3 years. You've got to do better than that. Sometimes you'll get support for a PhD, but you can't count on it. Is it only useful for long-term projects, they might ask? Will I understand it? That's one of the things that mathematicians are very bad at, in explaining what the answers mean in the context. And underpinning decision support is one of the key roles. They're always worried about intellectual property, The number of confidentiality agreements I've signed, I've lost count. I've probably broken a few at times, but so far I haven't been sued. We've had several reports at the last moment the companies have said, please don't publish that, the competitive advantage we've got will be lost. That's what IPR is, intellectual property rights. And then they'll rather quizzically sometimes ask me, why are you bothering? You've got a good job. Why should you bother? Well, I think the health of mathematics is actually at stake here, because if mathematics gets divorced from its applications, we'll lose too much. And this is one way, it's keeping in touch. Now, when you're doing this planting activity, there's lots of different things you can do. You can create interdisciplinary research centres. I guess my centre's one of them. And as you'll see from those reports, they're growing like crazy around the world. The OECD report led me to that statement in my article that industrial mathematics is on the crest of a wave. It's really taking off. And that's perhaps why the OECD took the action it did. Some departments, and I'm lucky to be a professor of industrial mathematics, have designated positions. And so I know one or two groups are considering having whole departments. I wouldn't actually recommend that. I think actually it should be embedded in a larger group. But certainly secondments of positions is very popular in the UK. And the Occam group has industry people coming in and they're going out to industry. Special workshops like our one that many of you came to, the study groups, and I'm pleased to hear from Kilquan that maybe there'll be one here one day. We look forward to coming, don't we? You can have special workshops. 2 weeks ago I co-hosted a workshop which was called Mathematics in Health. And it's largely untouched by mathematics health problems. I think that's certainly an area where there's some relatively easy problems around, and because they haven't talked to mathematicians very much, and they need help. All our cancer work now is being used as an underpinning mechanism for testing the efficiency of the so-called wonder drugs for treating cancer by chemotherapy. And they are now being used in some countries, some of those drugs, not in New Zealand yet, but certainly in the United States. So, you know, there's the opportunity of running focused workshops like that, mathematics and health. I'm currently got a contract to work in epigenetics. You heard of that word before? What does it mean, epigenetics? Take the word genetics and put epi in front. What's it all about? I'm maybe becoming an expert too quickly, but it's about how our genes modify themselves in early life. We get the footprint of our genes from our mother and father, but they express themselves differently in early life, when you're a fetus and right up to puberty, and it affects the quality of your life thereafter. Now, some genes shut down too early because of the environment. It's called becoming methylated. Some methyl groups have attached themselves to certain genes and shut them down. Now, if they're a bad gene, that's good. But if they're a good gene, like one that regulates cognitive development or something like that, it's bad. It's shut down too early. The brain's going to give up sometime, but you want to get it fully developed. And we've got some knowledge of some families that have children who are impaired in some way, and it's because of the genes did not express themselves long enough or well enough. That subject has been rapidly becoming mathematised, and I do have a current research grant to work in that area of gene methylation. And, you know, just look around you and you'll find there are burgeoning subjects like that. Now, education and training. I think a revision of the whole curriculum and content approach needs to be undertaken. And I've just come from a mathematical modelling workshop in Singapore, which had maths educators all around the world talking along those lines. I think we should be forming joint teams between industry and us. We should have positions that are called translators, who are people who go to industry to talk about what's going on, the appreciation of it, and then come back and engage some academics in the solution of those problems. The web has made a marvellous access for information about problems. I've already mentioned that, and centres of excellence and so on. And we should be sharing things like model agreements on IP, because you get wound up with all this going on. I think the academic infrastructure should be changed to support more interdisciplinary activities. The universities that us three belong to do have interdisciplinary groups. I'm with statisticians and computing people. Mark is the same, I think. And Bruce, you're also with physicists and chemists, aren't you, in Palmerston North? I think that's actually good rather than bad. The splitting up of these disciplines, I think, is a mistake. I think industry needs to look at itself a bit more. The need for the availability of positions in industry for qualified researchers. It's part of their obligation to the community to do that, and I keep nagging them about it and asking for money for them to do it. There needs to be a lot more national and international coordination. I think the OECD group was good, but it's now being wound up, and it'll probably just be filed in the dusty bookshelf. But I think we should keep that sort of thing alive. I know John Ockenden, who was chair of the experts group, has that in mind. I think we should be much more collaborative and less competitive. I've tried to make our centre a national thing. Massey University has got 3 campuses through the country, and that makes it a little bit easier. But when you run study groups, it's quite good to have it under the auspices of a professional society. I know I've said this here before, because then everyone will feel part of it. And you'll get more critical mass as well. Now, this is my big success of the last few weeks. We've convinced the Malaysians they should do it. And they are very pleased to have this announcement, which I can leave here. Some of you may want to go down there to it. It's not as close as the very good Chinese one, which was last December in Hong Kong, but I'm already pleased to see Mark's holding it there in his hand, that they've got half a dozen quite good problems lined up, and they're going to run it much like the ASEAN one there. So look at those times and see if you could go. I'll be glad to see you. I'm actually meeting them again on Tuesday in Singapore. Zainal Aziz has got the same fire and brimstone about it as I have. So take note. I've got copies of the brochure if you want one. So that's the first half of my talk. The second half, I thought I would show you a rather unusual study group problem. And one of the reasons I took up Yong John's invitation to talk about this is that it was one of the hardest problems I've ever come across where the mathematics was far from clear. We spent half the week trying to find what the mathematics was all about. The organisation was a defence organisation, DSTO, Defence Science and Technology Research Organisation, and the staff members involved, particularly Simon Goss, was antagonistic towards mathematics. I was surprised. He said, don't put numbers on these things. He said, I just want linguistic variables, he said. He wanted to describe things as strong, weak, not so strong. And I said, well, why can't we put a number scale on it and then translate it back? We spent half the week basically arguing about that. It was quite frustrating. However, we made some progress. I'm going to just tell you about the formulation of the problem because time will prevent me giving you all the solutions, and there's more work to be done. Like all these study group problems, you don't get them done in a week. It wanted influence diagrams. Directed graphs with weights, which would be basically a translation, and you have diagrams like that. Now, this may be very relevant to career if you're contemplating fighting someone. I hope you're not. But this is the kind of diagram we used. Just look at some of the boxes. It's like a flow diagram, so you've got these ones indicate a decision's got to be made. You've got your government, you've got the opposition, you've got the population, you've got third parties, you've got perhaps nations developing nuclear weapons, trade sanctions. Now, this was not done with career in mind, please note. It was Australians gave us this, third-party governments, case for war, Western governments, and so on. And if it's got a plus on the arrows connecting them, if it's got an arrow connecting it, means that there's some influence being conveyed from one box to the other. So, if there's a plus there, it means the influence is positive, and if it's a minus there, it means the influence is negative. So a third-party government making a case to the ruling government that there should be a war, perhaps it's negative. Now, that's about all they said. Yet someone had convinced them they should talk to his mathematician, so they brought it along to a study group. Now, what would you do when you got all that? Of course, we had to think rather hard, Winston Sweetman, Hayden Cooper and myself, to see whether we could give some underpinning methodology. Now, the first argument was the one I already mentioned, that you had to try to convince the owners of the problem to put numbers on things. So you've got to put values in these boxes, and you've got to put weights on these arrows. And so, you know, if you want to see the effect of some Western governments on your own government, you'd have to track through this, and you know, because this one isn't connected directly to that one, so you've got to go through. So there's an adjacency index there. So perhaps the graph theorists would have got through this quicker than I did, but we made some progress. And of course we have to introduce a little linear algebra. I'll jump a little bit because I haven't got too much time. We had to define a bunch of terms and quantify it. So we had to give quantitative measures to those boxes that we've got there. So the value of trade sanctions, so on. You know, you've got the sanctions against North Korea now as a result of what they did to you people, and that seems fairly justified, doesn't it? So you've got to put weights on these things. The owners of the problem from DSTO put quite a lot of opposition to doing this. As I say, they wanted to call things influences strong, weak, and we had to quantify those and then translate them back when we wrote the algorithms that I'm going to talk to you about. So we have a bunch of terms. We give weights to the nodes and have a collection of all those, and they may be weighted, have a real value, and it has to be converted from the linguistic scale. Poor old Sam fought that all the way. He said, I'll never convince the bosses in the army that we should do it by numbers. But perhaps that's why, perhaps they should. We've obviously got, and it doesn't take you long, whoops, it doesn't take you long to think of this, we've obviously got adjacency indicators. Aij is 1. If there's a... The A's are coming out a bit funny, aren't they? Never mind, they're meant to be A's. Are they okay on the screen? Oh, they're not too bad. Yeah. Sometimes different computers garble things up. A directed adjacency indicator. Aij is 1 if there's a directed path from xi to xj, and 0 otherwise. And so we've got that matrix of A's, which have got 1s and 0s. It's one of the nice there, and it'll be a symmetric matrix. Then we've got an influence measure. Now again we had to put numbers on those. Gamma ij is the influence of node I on node j. Now it took us a few days to get this far, particularly with the opposition from the problem owners. And it indicates the parity and the magnitude of the influence. Right? So it could be negative, if it's a negative influence, or it could be positive, and but it was always a real number. Now that won't be a symmetric matrix. So we have an adjacency matrix, and I called it an influence matrix. Now we may be reinventing the wheel. I know Bruce knows a lot about graph theory, a lot more than me. You co-authored a book on it, didn't you, with Charles?
Oh,
yeah. So you should have been there in Melbourne in February. We needed you, Bruce, and you were probably on a mountain somewhere.
I was, actually.
Yeah, I'm not surprised. So we managed, when we looked at these typical problems, to come up with an adjacency matrix and an influence matrix. And that was the means by which we looked at the progression of influences. Now the word progression came up and suggested an evolution of time was going on. So you can see now how my eyes lit up. There must be a dynamical system in here somewhere. So that's what we did. And in the software that we developed, it was actually done before by iterating in time to let's see how it settled down. And the guy that did this was a graph theorist, a chap from AMU. And then I actually realised that he was just in fact using a discrete dynamical system. And I'll show you that in a moment. And then, of course, we made it continuous so we could use some of the nice theory. But you can leave it discrete if you want. So we get powers of these matrices, AM and gamma M. And so gamma M will be M steps ahead of time. Sorry, M will be the steps in time. So that enabled us to get a systems appearance. Because if you want to update the weights and the nodes, you use the, I'm not used to this, I'm sorry. So you update the values in the node 6 months later, see what the state of the nation is, the old ones, and then some step in time delta, and using the obvious gamma JI xj. That should be lowercase x, I'm sorry. And of course, you can see that then quickly becomes, if you let the interval of time shrink to 0, that quickly becomes the dynamical system of this form, the transpose of the influence matrix X with the n by 1 vector and a given initial state of the Earth, as it were, x of 0. So, now please note that took a whole week really to unfold. But that's the kind of thing we managed to give back, and of course the associated algorithms for MATLABing. And it came out quite well. We were pleased about it because it meant that the solutions were easy to spot, because all you really needed to do was to find the eigenvalues of the influence matrix transposed. And of course the solution will be dominated by the eigenvalue with the largest positive real part. And I just about convinced the army that that was the way to go. We've got to go back to Melbourne in August to update this, but this is where we got to in February. I think it was pretty neat, actually. And when we were discussing it after the workshop, this is what we said in February. The algorithm is done. Okay, guys in the army, all you need to do is to find the influence matrix, put the numbers in the gamma, find the eigenvalues and vectors of gamma t, and the long-term solution will be that where lambda is the largest eigenvalue, or the eigenvalue of the largest real part. And the pattern of influence over your supposed diagram, like we had before, remember this? Whoops, I'm going the wrong way. You know, how it will evolve, how the situation will be in a year's time, can be got from the solution there. Now, you might think we could have done this differently, but this is what we did. Now, you know, that's pretty interesting, but then they said, well, some of the effects may be non-linear. So now what we're doing is saying, well, the drivers could be influenced by the state. Oh, when will I learn? The drivers could, this driving input could in fact be dependent on the state of the system. And we tossed that around a bit and came out with, this is the kind of pattern you want, a kind of logistic effect in n dimensions. And so the system that we don't know what the C is, we'll do a bit more work on the vector C, but that should be lowercase x again. So the evolution of the influence diagram will come out with this kind of problem. And of course, no longer have you got the exact solutions to play with. It's if you like, it's an n-dimensional logistic. So that's the kind of thing we want to look at. And of course, you might say, why you've only got the sum of the squares here of the xi's? Well, you can put a matrix in the middle too, if you want. So the opportunities for some new mathematics are endless there. Well, I just wanted to show you that rather unusual study group problem. I've actually been involved in about 30 study groups over my career, and that was the problem I think I found the trickiest, because it wasn't clear on the Monday where the mathematics was, but by Friday we got to what we showed you, and lots of simulations were done. I wasn't allowed to show you the simulations because, of course, it's a military secret in Australia. Well, I'm going to rest my case. I've done two things. I've talked about the planting activity, and I hope you enjoy reading my article. It's certainly, since it came out 3 weeks ago, my email box has been full of discussion about it, and it looks like I'll have to write another article with the feedback. It's a bit like a letter to the editor. And then I thought I would share with you that little insight from a study group problem that was more than unusual. And of course, I rest my case that it's not magic. Maths and industry is a real good combination, and it's unbeatable. I'll stop there. Thank you.